In this lesson, we study the problem of compatibility of a linear system of inequations. We may have several cases. No solution, a unique solution, and infinitely many solutions. Here we address the question of whether there is at least one solution. To study the compatibility of a complete linear system of inequations, the case of a particular system will be considered first, demonstrating later that any system can be written in this form, with which the general case will be solved. This particular system is of the form in this slide, which is a system in which the restrictions are equalities and all the variables are non-negative. To study the compatibility of this system, we write it in a different form, as indicated, which expresses the vector column of independent terms v1, v2, vm as a non-negative linear combination of the column vectors of the system coefficients. Therefore, the system will be compatible if and only if the vector column of independent terms belongs to the cone generated by the column vectors of the inequality system, indicating how to solve the compatibility problem. It is obvious that the two systems are equivalent, because if in the lower one we make equal each of the components of the vectors in the left and right hand sides, we get the above system as illustrated in the figures. So we see that the systems in the upper and lower parts are equivalent but written in a different way. Then, if the system has a solution, the vector v1, v2, vm belongs to the cone generated by the other vectors, because the conditions for x1, x2, xn of being greater or equal 0 restrict the coefficients so that they cannot be any real but non-negative real numbers. Otherwise, the system is incompatible. Therefore, we have converted a problem of compatibility into a problem of a vector belonging to a cone. To illustrate, we consider the following example, which is a particular case in symbolic form, because we have used as independent terms not particular numbers but letters A, B, C, D. How to check if this problem is compatible? To see if the system is compatible, it is enough to see if the column vectors A, B, C, D of the independent terms belongs to the cone generated by the column vectors of the coefficients of the system. That is, if it belongs to the cone A sub phi, indicated there. These vector generators are 1, 0, 2, 0, 1, 1, minus 1, 1, 0, minus 1, 1, 1, minus 1, 1, 0, 1, and minus 2, minus 1, minus 1, minus 1. To analyze the compatibility, we need only to obtain the dual cone of the cone A pi generated by these vectors, which is h sub pi, as indicated. H pi has been obtained using the algorithm, which provides the tables below, where we have introduced the 5 vectors, one per table, and we have pivoted 4 times in iterations 1 to 4, but we could not pivot in iteration 5. Then the final table shows that the dual cone has no vector space part and that the acute cone has only 2 edges. What condition must be fulfilled for the system to have a solution? For the system to be compatible, the vector ABCD of the independent terms multiplied scalarly by the generators of the cone h pi must be non-positive. So, if we force the vector of the independent terms multiplied scalarly by the generators of the cone to be non-positive, we get the indicated compatibility conditions. These are the two conditions that must be satisfied for the system to have at least one solution. With this, we have solved the problem for the particular problem stated. To study the compatibility of a complete system of general type with inequalities less or equal to, greater or equal to, and equal to, and with unrestricted variables in sign, we rewrite the system as in the form used for the particular case, proceeding in the following 4 steps. First, we replace each inequality greater or equal to with an equality, by simply subtracting a new virtual non-negative variable, 1 per each inequality. Second, we replace each inequality less or equal to with an equality, adding a new non-negative virtual variable, 1 per inequality. Third, we replace all non-positive unknowns with others equal to themselves change sign. And fourth, we replace all unknowns xi non-restricted in sign with a new variable x asterisk minus x0, where x0 is a common non-negative unknown x. Francisco Jubete has demonstrated that we can use a common unknown x0 for all of them. To illustrate, we give one example. Suppose that we have the linear system that you have there in the figure, where the independent terms are symbolic, that is, we use letters A, B, C, and D. Note that there are inequations with greater than or equal to relations, inequations having less than or equal to relations, and equations that use equality relations. Those that have equal relations we do not care, because the required system permits only equalities, so that they meet this constraint. But when we have a greater than or equal or less than or equal relation, we need to change them. So what can we do? Well, let's see. In the first equation, as it is greater than or equal to, what we need to do is to subtract a new non-negative unknown, which is x6, to force an equal to 0 relation. In the fourth equation, where we have less than or equal to d, we add a new non-negative unknown, x7, for it to be equal to d. With this, we have already solved the issue of equalities. And now we know that C, the last equations, x1, x2, and x5, are greater than or equal to 0. But nothing is said about x2 and x4, what means that they are unrestricted in sign. So, we replace the unknowns x2 and x4 by a difference of two non-negative unknowns. x2 will be replaced by x2 asterisk minus x0, and x4 by x4 asterisk minus x0, where the x0 is the common unknown subtracted to all of them that need it. Then, after these replacements and posterior simplifications, we get the equations that appear there. This system, which is equivalent to the first, already has all its equations written as equalities, and all unknowns, all of them, are non-negative. Then we are in the previous case. To see if the system in the slide is compatible, it is enough to see if the vector of the independent terms A, B, C, D belongs to the cone generated by the column vectors of the coefficients of the system, that is, if it belongs to the cone A pi indicated. Therefore, we have to obtain the dual cone of the cone A pi indicated. We do that with the algorithm introducing the first, the second, the third, etc., and so on to the eighth. And finally, we discover that only one vector remains, which is a W vector. Thus, this cone has no vector space part, but has an acute cone part with a unique edge. For the system to have a solution, the dot product of the ABCD vector and this edge vector must be less than or equal to 0, and therefore the condition is that B minus D must be less than or equal to 0. That is, B must be less than or equal to B, which is the compatibility condition. With this, we end this lesson. I hope, as usual, that you have been interested in the findings, and that you have discovered the power of having an algorithm to solve problems as complex as this one, in which even since the independent terms are letters, that is, we have dealt with symbolic, non-numerical problems, we can obtain a solution. With this, we end this video and invite you to see the next one.